Hello, everyone, and thank you for joining us today. My name is Jordan Larson, and I will be your host for this NASA Technology Transfer Program webinar on the Internal Friction Reduction Tool. Our presenter today is Joseph Cobb. Following Joseph's presentation on this technology, I will give a very brief presentation on how NASA licenses technologies to outside organizations. Before we get started, I'd like to point out that your microphones will be muted throughout the presentation. So if you have any questions, please type them in the chat box in the lower right-hand corner of your screen, and we will answer them during the Q&A session at the very end. Joseph Cobb holds a PhD in mechanical engineering from Mississippi State University, where he graduated with the top of his class. He worked at Energy Nuclear before starting his successful career at Marshall Space Flight Center as a materials engineer. Joseph specializes in severe plastic deformation processes, including friction stir welding, and has developed many innovative techniques that have vastly improved the industry. So at this point, I'm going to turn it over to you, Joseph.
Well, good afternoon, everybody. My name is Joseph Cobb. I work as a mechanical/weld engineer here at NASA at Marshall Space Flight Center in the Materials Processing Group, EM32. Today I'm going to be talking to you about a new design for the self-reacting friction stir welding tools to reduce the internal friction in that device. A little bit about myself. I got a PhD from Mississippi State University in mechanical engineering, professional engineer here in the state of Alabama, and work in the processing group here. A little bit about what our team does. So we develop weld processes for flight hardware, and we also build some flight hardware here at Marshall. Specifically, we're working on launch stage vehicle adapter and the MSA for the SLS. And we utilize extensively both conventional and self-reacting friction stir welding on most of our projects. So we do a lot of that work, a lot of research and development into not only solid state joining, but also typical fusion welding as well. We also lead risk reduction efforts for welding processes on the SLS rocket. So just an overview of what we're going to talk about today. So we'll start with the motivation, so why we care, what the internal friction reduction tool is, like a design overview of it versus a typical standard self-reacting friction stir weld tool. We'll talk about how we measure the internal friction, because that's a big issue. And then we'll go over the test plan that we carried out to evaluate this tool, the results that we got from it, both from a smaller 30-inch panel level study, and then also full-scale hardware that we've welded with this device. Then we'll wrap up with conclusions. And a fun fact here is that the average engineer burns 170 calories a day jumping to conclusions. So get your exercise in and jump to as many conclusions as possible. All right, so why do we care? So when we compare self-reacting to conventional friction stir welding, self-reacting has a smaller parameter window, increased defect rates, and larger standard deviation of mechanical properties. So this decrease in robustness compared to conventional friction stir welding causes increased rework rates for us, limits our maximum continuous weld length on some schedules. So time and money, right? That's why we pretty much care about everything, time, money, and performance. So typically what we see in self-reacting welds, and then this is more schedule dependent, depending on which set of weld schedules we're running, alloy, material, pin tool combinations, right? But in general, we see indications begin after an intersection, right? That's the most likely spot we'll see indications. And with some of our weld processes, they'll become more and more severe as the weld length increases. And also to the point where we'll start getting defects in acreage, and these defects can become larger and larger and longer, and eventually, in some cases, have opened up and just ran continuously. And as part of a sensitivity study that we were looking into as a part of a root cause corrective action for a defect that we had on one of our welds on the rocket, identified load shunting as a potential sensitivity, right? So the amount of load that we apply when we're performing a self-reacting friction stir weld isn't necessarily what we're getting down at the pinch zone. And so we'll talk about that a little bit more on this slide right here. So what I'm showing you here is just a section view of a typical self-reacting friction stir weld tool, which is what we're going to call our standard tool on the left-hand side here. So we have our crown shoulder that fits up in your tool holder. And running through that crown shoulder is our weld pin, which is rigidly attached to the root shoulder. So as we pull up on the weld pin, root shoulder is pulled up against the material and creates a pinch force on the crown shoulder. So all this co-rotates together, and we have a little cavity right here, right? So we've got a counter bore on the inside that turns into a very tight toleranced diameter right here. So these are very close in diameters between the pin and the crown shoulder. And then this high tolerance zone here, that's what supports our pin as we're welding, and it keeps it limits the amount of material that wicks up in here as we're making a weld. But material does wick up in here, and so as this material gets wicked up into this between the pin and the crown shoulder, it causes internal friction, right? We've got aluminum that's coming up into here, potentially some intermetallics forming, and so the more aluminum we get in here, the larger the surface area and hence friction that we have between the pin and the crown shoulder. And since we're applying our load up here, any internal friction that we have down here can result in load shunting, right? So we pull in 4,500 pounds on the pin. We're running over an area where the root shoulder needs to come in some. So we think we're pulling with we have 4,500 pounds of pinch load, but what we really have is 3,500 pounds of pinch load because we're losing 1,000 pounds due to internal friction between the tools. So the modification in tool design with the IFR tool is we've taken that, and instead of having one large support right here to support our pin, we have a very small area down here on the bottom that's supporting the pin, along with a upper support up here, and there's an internal cavity. I don't know if you can see the green on your screen right here, but if you see this green portion, I just painted the inside of the crown shoulder before I cut it, and so that's actually an internal cavity, and in this particular model, we've got some windows in the tool, so you can see in, and it lets material out, although we don't have any issues with filling up the tool over the course of a weld. And so the theory behind this is that we've limited the area that we have for internal friction to happen, right? So we've limited that surface area for the tool to bind on. So once the aluminum wicks up through here, so once it's gone up here into the cavity, right, we've got our maximum amount of friction that we'll have on the tool, and we've limited the surface area to where that amount of friction is negligible, can be neglected, in our friction stir welding process. So here's just a cutaway of the shoulder, because in this particular design, that's where we have all the, this is the business end of our tool where the changes are. So the green is the larger diameter bore, and then the red is that high tolerance zone where we have our internal friction. So if you see on a standard tool, and I've had to, due to ITAR restrictions, right, take away any dimensions and non-dimensionalize all the test results here, but we should still be able to get all the details that we want out of it. But so with a standard tool, we've got this long continuous zone. So as our aluminum continues to extrude up in this tool, we're building up more and more friction as we go. Whereas with the IFR tool, we build up a little bit of friction as it passes through right here, and then no additional friction, encountered. We've hit our max friction, and we've limited this area right here to a small enough surface area that amount of friction is within our weld parameter set. So how are we going to measure this internal friction? Because that's really the issue, right? So we've got in typical self-reacting, right? We don't know how much load shunting is going on because we have no way to measure the actual pin force. And so if we know how much internal friction we have in the tool, we could, even if we just know that post fact, right, we could kind of get an idea on what's going on in the weld and if this is actually contributing to, because of our weld defects, this load shunting, right? So we don't think we're pinching with either too much or too little load, depending on which way if our material is getting thicker or thinner, if our shoulders need to come closer together or further apart. And either one of those, if you go too far on each side, could cause a weld defect. So we measure the internal friction. This is on panel level. So we're welding in load control. We'll change over to position control right before we come off the end of our weld panel. We'll come off the end, and as soon as we clear the end of the panel, everything's still hot, right? We'll eject this pin downward, and we're still recording forces. So if this is a clean pin, right, if you just took a new pin and you push the pin downward, there'd be no force. There's nothing between it, right? The pin and the shoulder slide freely between each other. But after we get done making a weld, it does take a certain amount of force to push the pin down, and so we can measure that, and that'll tell us we're right after we come off the end of the panel. The tool's still hot. Everything's as close to as it can be during the welding process. So, and that's what we use to gauge how much internal friction we have in our tools on a panel level. So a barrel's the same way, except the barrel, so normally we use self-reacting friction stir welding to do circumferential welds, right? So we can't run off the end of our barrel because it's 360 degrees. So we'll have the internal friction will resist pushing the tool out, along with having to push through the material, the barrel material that our pin is in intimate contact with when we're welding. So the ejection loads for a barrel are just a little bit different, and we'll look at that in the data results, but there's internal friction plus the force of pushing through our weld material. So just kind of go over the test plan and what our hypotheses are going in, right? So we think that we have defects that are, not all our defects are caused by internal friction, but we think that that's a potential sensitivity that we have, right? And so we want to go in and weld short panels to validate the IFR tool works, right? That we're actually getting a reduction in internal friction. And then for the large scale barrels, we developed a weld schedule that was close to what we use in production, but we went on the low side of the pin load, right? So on 30-inch long welds, we were getting good welds, but the pinch force that we were applying, that pin load, was on the lower side. So if we started going much lower than that, we'd get defects. And so we said, hey, if we do this, we can go look and see. We'll kind of be on the edge, so we'll get good. So hopefully we'll go weld a large scale article, right? We'll start out clean. If internal friction is contributing to what we're seeing here, we'll start out clean and we'll get defects that will get progressively worse as our weld length increases. And we'll make a weld on large scale article using our standard tool for a baseline, and then the IFR tool, and note any differences that we find. And we're looking for, success criteria as reduced volumetric indications, better mechanical properties, and any differences that we see in machine feedback. So here are ejection loads on 30-inch panels. I've had to non-dimensionalize this data right here, so it goes from 0 to 1. But the scales are the same here, and we're talking about thousands of pounds up here to push this pin out. And when we look at how the pin ejection loads go by weld, so this is number of welds on the self-reacting tool assembly. So our first weld, we're down, this is actually below 1,000 pounds, but we can see that this ejection load keeps climbing as we're making more and more welds on the tool. And so this is just force feedback from the pin, and I just cut off the weld portion that happened before this. So this is just a portion where we're running off the end of the panel and shooting that pin tool down. So I've just snipped that from here. And so with the IFR tool, we see that we have lower loads for all of our welds than even the first load with the standard tool, ejection loads. And we're on welds. We did some really short startup welds previous to these weld numbers. So I started just with our full length welds, which was weld 8 on the tool, and ran to 14. And you can see that really good results with regards to ejection loads and hence internal friction in our tool. So the IFR tool is, limiting the amount of stiction that we have happening in between the crown shoulder and the pin. So I talked about welding large scale articles. So here's a layout of the barrels that we actually welded. So we took a barrel, we cut it in half, and we split the intersections so we get more intersections to go through, since that's where we normally see our weld defects. We welded 360 degrees around. We had a small overlap section right here where we came and passed through our startup region. And then we cut 12 inches out of this barrel right here, and we just dropped the top barrel down, and we re-welded it using the IFR tool. So that's the setup there of what we did on the large scale hardware. If we look at ejection loads for the large scale hardware, we made these two welds first, right here, the 1,060 inches. That's how long our welds were. Then after we got done, we made a couple of more welds with the standard tools on a couple of different studies, but I pulled that data in from here also. And so what we see is, this is non-dimensional data here, but when we made a 6-inch weld with a new tool, this is the ejection force that we got on some of our startup development. And we didn't see any change at all in ejection loads for our 1,060-inch, long, large-scale weld with the IFR tool. Whereas with this tool, just for reference here, so we're looking at almost 10,000 pounds up here. So the machine actually, once we push that pin outward and the tool cooled down, the pin actually was stuck to the crown shoulder so bad that we couldn't actually get it apart. We stopped the machine trying to move the pin tool, and it just wouldn't come out, period. So it was completely locked up. Once it cooled down, the machine wasn't even able to move that tool. And we get a fairly quasi-linear, there's not a lot of data points here, so a few more might help us, but almost a straight line here in terms of internal friction buildup with regards to weld length. So we can see that that's continuing to increase as our weld length increases for the standard self-reacting tool, main takeaway IFR tool, constant amount of friction in the tool. So next, let's look at the X-ray results we got from making those welds. So what I've got laid out here is the standard tool on top. So we went in and sectioned, took out sections of the barrel and had them X-rayed. And some of these, we took out the intersections and X-rayed those. And then we also had some acreage areas that we also X-rayed. And so up top, this is just how many inches we are into the weld, and then also how many degrees in terms of 360 we are in the weld for these areas. And these are the exact same locations. This is the weld made with the standard tool, and then on the bottom you'll have the weld made with the IFR tool. So 8 to 25 inches in the weld will start out clean, no indications for either tool. Next we moved to 153 to 178 inches into the weld, and we don't have any indications in either one of the welds still, both clean. So 240 inches into the weld, they noted an inclusion, but that's not something related to a parameter defect in the weld process. It's just an inclusion there, nothing that would indict the weld process. IFR tool still clean. And then once we get 285 inches into the weld, this is right past an intersection. I don't know if y'all can see the light area. There's kind of a light band right here. So this is our intersection coming up from here on the advancing side. And there's they call it 1-inch wormhole noted here. It's very, very faint. When I was looking at it with the NDE tech, I couldn't really see what he was talking about, but he swears that there's a very, very small faint wormhole here, an indication noted. The IFR tool is clean in this location. And then so about 500 inches into the weld, this is also at an intersection. When the intersections are on the retreating side here, you can see how the tool kind of deflects over just a little bit crossing the intersection due to the softer material here. But in this area, a 1/2 inch long wormhole noted. At the intersection, probably still pretty hard to see on your screen. When I was looking on the screen over at the lab with X-ray tech, I could see it on there. It's a little harder to see in the PowerPoint here. But IFR tool, no indications noted. Then we move over 550 to 573 into the weld, inches into the weld. We've got a 1.3 inch long wormhole in the standard tool. Nothing with the IFR tool. This is maybe still hard to see here, but this wormhole is becoming a little bit more severe as we're going through here. It's easier to pick up here. I don't know if y'all can see it, but it's kind of this speckle pattern here, and there's a little bit of a line there. Then as we move about 630, 625 inches into the weld, I actually had to break this panel up into 3 sections. So this is acreage before an intersection. They noted a defect here, or possible wormhole is what they called it here. So there's a potential one here. There is a 3/4 inch long wormhole indication here at the intersection. And then also there's a 5/8 of an inch long wormhole after over here in the acreage. So this is a measuring stick that's through here. So on the panel length, you know, some panel was cut off here. So 5 inches, 6 inches into this panel, our possible wormhole, we're centered up here at 12 inches on our intersection, and then 21 inches over here, another indication noted. IFR tool's clean for here. And so we'll see these indications, they actually get progressively worse as we're going through here. So this is a 1.3 inch long wormhole, a lot easier to see here. Severity's increasing. Right after an intersection for us here, IFR tool clean still. So this is actually just some acreage right here, an acreage pen that we pulled out for some other testing. And we see we've got a 1.8 inch long wormhole here in the standard tool, very pronounced. Nothing noted in the IFR tool. So now we're about 800 inches in the weld, or about 280 degrees from the start of our weld. There's another, so this is after an intersection right here. Another defect noted here, so 1.8 inches long, pretty severe. At this particular intersection, they called a 1 inch possible wormhole. So we're real faint. This is one of those that was like the indications we saw at the start. Like I really, you know, with the standard tool, I really couldn't see what they're going on here. They tell me it's there. So they called a possible wormhole at this location. And then as we move to about 900 inches into the weld, or 300 degrees, this is one panel. I had to kind of chop it up so we could get all the kind of an enlarged view of the defects just due to aspect ratios. But they've got a 1.3, 1.4 inch long, pretty severe wormhole here. Before we get to an intersection, this is just acreage. And then at our intersection, another 0.9 inch wormhole here, pretty easy to see. And then a possible start of wormhole called about 19 to 20 inches into the weld. And with the IFR tool at this particular intersection, so it would correspond with this location here, called 1 inch of possible porosity or wormhole noted. I'm copying the terminology here for all of these that they called out in the X-ray report. So those were the only defects noted for the standard tool. We've still got plenty happening, or for the IFR tool, we still have plenty happening with the standard tool. So these are getting longer. So this is a 2.5 inch wormhole right here, possible starter wormhole previous to it. Here's our intersection here. Clean with the IFR tool. More the same here. We're 334 degrees into the weld here, so we're another 2.5 inch long wormhole here, and this is before our intersection, and then at the intersection, of course, another plus 2 inch long wormhole noted. Nothing with our standard tool, with our IFR tool. So next we're, almost 1,000 inches into the weld, or we are 1,000 inches into the weld right here. And right after, I believe this is, maybe it's not an intersection. I have to go back and look at this one, but another 1 inch long wormhole noted here. Nothing with the IFR tool. Then we had a really large wormhole noted here, where we just kind of opened up into kind of like a tear right here. So this is 8.4 inches. This is all the same panel. I just kind of had to box it to get it all in here. So for this section, they called wormhole right here for 8.5 inches. And then this is following that portion they called possible wormhole after that. So we're going from about 13 inches total of indications and possible indications, followed by another 1 inch long wormhole towards the end of this panel. With our IFR tool, didn't note any indications there. And then here's our overlap region, so you can see where we start, where we had our startup right here. We come over that and then do our closeout, so we'll have an overlap region here. They noted a 1/2 inch long wormhole where we crossed over our startup region. And with our IFR tool, we didn't have any indications noted in those at that location. So just kind of sum up our total, right? So we had 21 indications noted in total for the standard tool. They started out very faint and got more severe as our weld length progressed, versus 2 indications with the IFR tool. So both very faint. So yeah, that's in terms of just linear inches of welds when you add those together. So there's 41 inches versus 2 inches, and we only x-rayed the sections of the barrel that we pulled out, so it wasn't a 360 degree x-ray of the whole barrel, but for the sections that we actually pulled out, 41 inches versus 2 inches of weld defect, and you could see the severity difference between the two. Next, we'll look at tensile data. So I've got cryo tensile data here, and so this is non-dimensionalized, and this is just a 20 KSI spread from 0 to 1 right here, just to kind of give you a sense of what we're talking about. We're assuming we're not starting at 0 KSI, but here's the spread of our LN2 tensils. So you can see definitely getting more scatter as we're going, as our weld length is increasing for that. And so we pulled the samples from the exact same spots for the IFR tool. So each, we sampled exactly identical for each one. And here's the LN2 tensile data, same scale, 20 KSI delta from 0 to 1 here. And you can see much tighter tolerance on our ultimate tensile strengths. So there's kind of an overlay between the two. You can see really tight, nice grouping for the IFR tool. Start out with good data for the standard tool, and it just progressively gets worse and worse. Elongation to failure for these samples, so the LN2 samples, this is what we're showing here. Non-dimensionalized data here, but this goes from 0 to full scale percentage of elongations. And we look at the IFR tool, a lot better uniformity in our results there, pretty good results for elongation to failure, very consistent with regards to that. So that's just an overview here showing the difference in elongation to failure for IFR standard tool at liquid nitrogen temperatures. Here's our room temperature tensile test results. So we went through and pulled room temperatures with it also. I do want to note that we didn't test the area of the intersections right there. So we had a 4-inch dog bone that we're using to actually test the intersection, and our damage tolerance folks wanted to save those and perform some additional testing on those for some potential stuff that they're looking at. They actually wanted some wormholes to test. So the actual wormholes that were in the intersections don't make it in any of this data because we didn't actually test the actual intersection. I don't have that test data right now, but our damage tolerance folks are working on pulling that, devising the test plan that they want to run on some of those wormhole samples. So, but yeah, just here, the rest of that data, you can see it clearly getting a lot of scatter and a lot of drop off as our weld distance increases. Oops, I went the wrong way there. So there's standard tool. Here's our IFR tool data. For the uniform, we've got one dropout right here. It might have had a little bit of paint in it, and we'll talk about the paint in just a second. But so we also did some thermal tests. We did quite a few different studies on this one weld at the same time, and one of those was a thermal study. So we had some thermography cameras, and we painted strips around the side of the barrels. And I believe a little bit of that paint, just looking at the fracture surface, may have worked its way into this particular sample, but I didn't want to cull it just based on that, since I couldn't be sure about that. But just looking at the fracture surface, it looked like that might have been a possibility there. But for the uniform, good data. This is not a full scale. This is also that 20 KSI range, I believe, for this one. Showing you there, and then I've got a graph coming up that's got it, full scale 0 to full strength of our welds showing up. But just the overlay, you can see the difference between the two tools. Then our painted region here. So here's an actual picture of the barrel as it was being welded. So we painted 2 strips, and we kept them just outside of where the weld tool was going to run, so that paint didn't get consumed during our weld process. And we had 3 regions on the barrel where we wanted to get as close as possible and see, hey, what's our temperature doing? So we painted actually the whole entire barrel. So we were welding through paint in 3 sections of the barrel, which I have highlighted in green. And so we pulled a few tensils from those barrel sections, those painted sections, just to see what was happening in the painted region. And then we also pulled a lot of tensile strips following it, just to see when we came back to what our regular weld process was doing. So we can see for this first painted region right here, our ultimates. So this was ultimate tensile strength right here. They drop way down, and this is actually full scale. So this would be, our average strength, and this is 0 KSI here. So we get a lot of drop here, and then our elongation to failures correspondingly go down with that. And you can see after we leave the painted region, we have one test point right here that's still dropped down low. But other than that, we come back up to our normal strength values very, very quickly. As we progress through here, we drop off again here. Then it takes a little bit longer. We've got a few more data points that have dropped out here. And then as we get towards the end of the barrel, you can see that we're starting to, it's taking longer and longer if we actually come completely back at all. With the IFR tool, we can see that we come back instantly at the start, middle, and end. So we're returning back to our nominal weld properties as soon as we get done with the paint. So definitely getting some differences there between the 2 tools and recovery from a painted situation. Not that you'd ever have that on a barrel, but just in terms of recovery from some non-typical situation, how fast you'll get back to normal. The IFR tool seems to be performing excellent with regards to that also. So just kind of wrap up the conclusions on what we've got. So with the typical self-reacting tool, our internal friction increases with weld distance, but that wasn't the case with the IFR tool. We saw that internal friction appears to cause issues with weld quality. So we were on the low end of our parameter window, but you can think about this in terms of a production sense when you're kind of in the middle, right? As that friction builds up, if you hit something where you have a little bit extra mismatch or something like that, and your tool needs to contract down, those type of cases, could really be a benefit there. If you drop, if your shunted load drops outside of your critical threshold window. And then the experimental evidence that we gathered here shows the IFR tool is able to address those issues.